Hello everyone, let's start. Okay, good afternoon again. My name is Gema Villegas. Thank you all for being here in this special session, in this webinar about DIAS environment. Today we are talking about the platform DIAS, or Data and Information Access Services, which centralize the access to Copernicus data and information. In GoToSpace Hub, one of our goals is to facilitate and disseminate the space technology, and DIAS environment is a key tool for achieving this objective. Our agenda for this afternoon. Jaroslaw, a member of technology partner in Poland and the leader of this task in GoToSpace Hub project, will welcome and introduce you to our key speaker, Professor Cupidura. Professor Cupidura will explain the DIAS platform and will talk about the open access to Copernicus data. After that, a space tour company will share with us their project based in Copernicus as an example of the possibility of use of Copernicus. And finally, last but not least, Elsa de la Haza will explain the DIAS Environment Hackathon, other relevant events around the DIAS platform at GoToSpace Hub project.
Welcome everybody. Thank you for attending our event. So I represent the Technology Partners Foundation, who is a partner in the consortium realizing GoToSpace Hub. Why we decided to arrange such a meeting as today? I would like to quote Aristoteles Onassis, the very famous person who owned a fleet of tankers, of oil tankers. The secret of a success is to know something nobody else knows. And we would like you, after the series of instruments of our GoToSpace program, that you will be able to know how to identify the opportunities, how to diagnose and assessment the situation, your business context, and your business development capabilities, selecting and implementing the actions, and then evaluation through the cause and effect of actions. In order to get this this capability, you need to know how to watch the Earth, and the key expert is here. Professor, the floor is yours.
Thank you very much. First of all, thank you for invitation and for this kind introduction. I want to say that not everyone in Poland live in attics, as we can see together with Jarosław. We have also some ground floors and first floors, not only attics. Well, now I'm a bit afraid of sharing my knowledge with you, because as Jarosław said, the key to success is to know something nobody else knows. So I don't know if, but well, maybe I will miss something and still keep some information for me only. I will start to present my first presentation. Okay, I think that's this one. Yes, that's the first one. I hope you can see it. Please confirm that you do.
Yes, we can. Yes, perfect.
Great. So I will start. DIAS training for business clusters. DIAS stands for Data and Information Access Services. We'll go to that at the end, almost at the very end of our presentation. But first, as Jarosław said, I would like to introduce some basic knowledge on remote sensing, because first of all, we have to know how to use those data, how to use this remote sensing imagery. About partners of the project, Creotech is one of the Polish leading, not only Polish but European as well, space sector companies. About Technology Partners Foundation, Jarosław already told you about. So I will move straight to the presentation, to the goal of the presentation, as Jarosław already said. I want to tell you something. Well, for these 2 hours, something about remote sensing, about basics of remote sensing, and to inspire you to some ideas, but also to get some ideas, some feedback from you. Probably, I hope you have some ideas, you have some already. You inspired something. You know your fields of interest. So if you do, please share it with us, because later on in the further stages of the project, we'll be preparing like a tailor-made like training workshops for you with our local experts. So if you have any ideas, please share with us in the chat box or in whatever form, email or evaluation forms, if there are any. So well, I will try to remind you that we need this information from you. So if you have any ideas, please ask them. Please, if you have any questions, please ask them. If you have any ideas, please share them with us. And yeah, and that's it. About this webinar, about this part, my 2 hours, it will be divided in actually 2 parts. The first part, the first presentation, will take like 55 minutes, I suppose. And after that, we will have probably like a 5-minute break, just to drink some water, whatever. And after that, we'll go to the second and third part of the presentation. So the first presentation, introduction to remote sensing and particularly optical imaging. After that, some important things about how to choose satellite imagery, so important properties of satellite images. And after that, some basics on on radar remote sensing, and also on other types of remote sensing data like thermal imaging and laser scanning. We will not focus on that, but we'll just tell a few words about how to use them, how they could be useful. Okay, so first of all, what is remote sensing? Probably you know. So it's getting information about objects from distance without touching them physically. We can use like aircrafts or satellites or balloons or whatever, actually, to get this information. But probably the most important question here is why remote sensing? Why this tool is so useful? So first of all, we can get a bigger picture, but literally bigger picture. So with an instant, actually, or with, well, literally in a few seconds, we can get image of like tens of thousands of square kilometers. So that's the first thing. The second thing, we can see more using remote sensing. We will talk about it in a minute, probably. And the third thing is relatively cheap data we can get from remote sensing. By taking like this whole picture of like, I don't know, like whole city or whole region at once, we can get this data quite cheap, relatively cheap. Of course, it's not cheap to build a satellite, to build a camera, photogrammetric camera, to send the satellite into space. Of course, that takes some time and money. But after that, we can use this data quite, well, cheaply, let's say. So even some data are for free. So we will talk about some sources of data as well. So how can we see more with remote sensing? Here we have a drawing of electromagnetic spectrum. So the whole electromagnetic spectrum, there is actually, well, everywhere, almost. This thin part here, this is visible spectrum. That's the only part we can see with our eyes. So from like 400 nanometers to 700 nanometers, from like blue to red in general. So only that we can see with our eyes. But a lot of information is hidden somewhere else. Like, of course, we can looking at something with our eyes again. We can see that it's red or it's green or it's yellow. We can tell that okay, turning vegetation from green to yellow means something, and we probably know what does it mean. But actually, a lot of information is hidden somewhere else, because as we probably know, like a condition of vegetation changes, the color of the vegetation changes as well, together with that. So we know that radiometric, that electromagnetic radiation responds somehow to the condition of the object. So there are a lot of different parts, a lot of different bands of electromagnetic spectrum that also respond differently on the conditions of the object. So this is how we can see more, like combining this information from visible spectrum, why not, but also from the other bands of the spectrum. When we can get, by taking images, we can get more information on that. Of course, we cannot see it with our eyes, but we can build tools, instruments, cameras, antennas, scanners, whatever, to get information, to take pictures, to take images, to get information, to get data about those different properties, different features of the objects of our interest. First, we start with optical range. Sometimes we can call it like visible plus infrared, so it's like VISIR. So this is this visible spectrum, but also some part, not everything, but some part of infrared spectrum as well. Okay, so the important question is how we know what we see actually, because we have, of course, like a vast experience with this visible spectrum. So we know that yellow means yellow and red means red, and what it means actually. But what about those different parts, different bands of spectrum, like infrared and etc.? So we learned something called spectral characteristics. We will refer to it in some parts of our presentation. So that's basically a function or set of functions showing us how different objects and different objects of different conditions reflect different bands of radiation. Like here, for example, let's look closely at this green drawing here. That's a vegetation. That's a spectral characteristic of vegetation. And let's start here. This is a visible part of spectrum. We can see in blue, we can see in green, and we can see in red. Sorry. So we know, for example, that vegetation is green, and it's green because it reflects more green than blue and red. So we can see it here. It reflects like, well, 18, 15, 20% of the radiation. So it's not much, but it's much more than of those other parts we can see here. Like maybe I will use this nice thing. Yeah, okay, that's much better, I think. So it's much more here in this green band than in blue and red band. So that's why we see that vegetation is green. But what we can't see is this part, for example, near infrared band. It's much brighter in this part, and we couldn't know it like, well, with our eyes because we can't see near infrared at all. But we can build a tool, for example, we can call it spectrometer, to like picture the vegetation and learn how much of this part of radiation it reflects. So that's how we know how to interpret those images we will see taken in this invisible parts, in the visible bands of the spectrum. What is also important here, like for example, this near infrared part, we can see here dry vegetation. So it will be yellow in reality, but what's important, it's much darker here in near infrared. And what's very interesting, this near infrared is very useful for evaluation of condition of vegetation, because it responds this part of the spectrum, this near infrared, respond very quickly to changes in condition of vegetation. Well, we can see that the vegetation is dry when it turns from green to yellow, but like after a few days maybe, or even dozen days. But here in this part, we can see it after like few hours, several hours. So it's very, very useful. Normally, we take those images, because we talked about different bands of spectrum. So normally to get the most like precise, exact information, we take different images in different bands. So here we have, for example, blue image. Of course, it's not blue. We can see it's gray, but blue image means in this case that it contains the reflectance in blue band of the spectrum. So only here, only this part we could enlighten it in blue, and this is how we could see it. So here we have a green band, well, a bit different, of course, because it's different band. Red image again, and what will happen next when we switch to near infrared image, we'll see that the image will be completely different, because this is completely new information in this image we can see. So here again, red, well, blue, green, red, quite similar, not exactly the same, but quite similar, and near infrared, completely different story. That's a completely different information. Enriching our knowledge on the surface, on those objects there, very much, really. And here another image of infrared, bit different, also called infrared, but different thing, different band, so-called short wavelength infrared or middle infrared. So we have much different additional information, complementary information, using those different bands. Of course, very rarely we use those single bands to analyze, to visualize this data. Usually use something called color compositions. To do that, we need 3 different images, or at least 3 images in general, and we put them, each image we put through one of the 3 like filters components, like a basic color components like blue, green, and red. So what we have here is like we have a blue band, this image containing information or data about reflectance in blue, and it's put through like blue filter, green band put through green filter, and red band put through red filter. So this is how we can see whatever was bright in blue is bright in blue in this image, whatever is bright in green is bright in green, and whatever is bright in red is bright in this image as well. And otherwise, of course, it was the same way. So whatever is dark, etc. So when we combine those 3 images this way, using this additive system, RGB, we create something called natural color composition, or true color composition, as you prefer. So why this is natural or true? Because every color here is a color we could see with our eyes, actually. So this is very easy to interpret, because, well, we're used to it. We're used to these colors. We know what does it mean that it's green, or this is dark green, and it's blue and white, etc. But actually, it's not very informative. Let's see how it looks, how it will look when we add something more, when we change this composition, and we add, for example, near infrared instead of blue. We had red, green, and blue. Now we have near infrared, red, and green. Of course, we don't have anything like near infrared color. It doesn't make any sense. So we have to choose one of those 3 one of these three basic colors to put this new infrared band through. So, well, we decide here, usually we do it this way. We decide to put new infrared through red component, red filter, and red through green, and green through blue. So we create something called false color composition. Well, definitely the false, they're not true, or color infrared composition. Sometimes it's called like standard composition, but I don't think it's used anymore. So it looks quite different, as you can see. So it's much more difficult to interpret for some unexperienced person. But when you have this experience, you will see that the information here is much richer than before, than in this image with only visible bands. How we can interpret, how can read this image? Well, let's look here. What's red in this image actually? Red means that it's a lot of red, not a lot of blue, and not a lot of green. So when we look how they were actually, maybe here will be better. So this one was put through red filter. So it means that whatever was bright in near infrared, whatever reflected a lot of infrared, was very bright in this red component of this composition. Okay, so when we see here, how we can see here, this vegetation reflects a lot of actually near infrared radiation, but it's shown in this image as red, and it reflects much less, a little of red band shown here in green, and green band shown here in blue. So it means that all of those red parts in this image are probably, well, actually they are vegetation. So this is how we know how to read those colors, and it's not very difficult actually. You just need some experience with that. And something even better, I think, when we use two different infrared bands, like here, we use also short wavelength infrared. This acronym stands for that. So we can see that we can see even more colors than before. So let's compare this color composition with this one. This is a true color composition. This is this false color composition with infrared. So we can see that like a number of colors, like amount of different colors here is much bigger than here. And actually every color on this image means different properties, different features, different condition of the object. So here, using this composition, we can learn much more on the object, on the surface, on the Earth surface, than using this one. Even if at the beginning this might be much easier to read. So this is how we can see more using those additional invisible, let's say, bands of the spectrum. Of course, optical imagery is not only those visible bands and infrared. It's not everything in remote sensing. You have also radar images. Radar, that's a completely different story. We'll talk about it. Thermal as well. We'll talk. Also, we can use laser scanning, but that will be like in an hour probably. First, we talk about those most important thing to consider when we decide to, well, when we choose imagery suiting for our like interests. So we have like 4 different general, the most important like features, like properties of the imagery. So let's start with spatial resolution. That's probably the first thing we think about when it comes to an image, to satellite image, to how detailed it is, how small objects we can see in this image. So this is spatial resolution. How small is the object, is the smallest object, or how big is the smallest object we can see in this image. Very often we misinterpret it as a pixel size. Well, usually when you go to some technical details on imagery, you will find something called GSD. That's a ground sample distance. That's the same thing as pixel size. So that's the size of this pixel. It is 1 meter, 10 meters, 20 meters, 100 meters, but it's not exactly the size of the smallest object we can see in this image. Those two measures are related, of course, but they are not the very same thing. So just to quickly like to introduce you how to learn what will be the smallest object we can see with, for example, 1 meter pixel. It will be like 3 times bigger. So to see the object of 3 meter size, we need 3 times smaller pixel, like 1 meter, and it's linear. So if we need to, for example, see the object of 10 meter size, we need like 3 meter pixel. I don't think we have time to like go into details why it is that, but just to remind you, just to you know, remember that this is not the same thing. Those two, let's say, those two measures: spatial resolution, the smallest object, that's the most important thing for us, and the pixel size, which are related but not actually the same. So if we need 1 meter objects, we need to have 3 times smaller pixel. Actually, 1 meter pixel will not be enough for that purpose. Okay, so just to like to have a review of how it affects the spatial resolution of the GSD, this ground sample distance. Just to remind how it affects the image, what we can see in the image. So this is an airborne picture, but we have VHR satellite imagery, very high resolution, VHR stands for, with even smaller pixel, so like 0.3 meter. So we can see in this image like shrubs, maybe bigger rocks. So it's very detailed. We can see actually everything we could imagine there. We couldn't read a newspaper, I suppose, but we could see a person probably lying in the ground without any details, fortunately. Okay, so this is a bit degraded to 1 meter pixel size, and again 2.5, 5. So we see how the details like disappear from the image. 10 meter Sentinel-2, very important for us because it's a part of the Copernicus program. So it has pixel size 10 meters. So it will be looking like that. 15 meters Landsat, 30 meters also Landsat, but multispectral. We will talk about it in a few minutes, about this multispectral things. And for example, Landsat MSS would look like that. The image of Landsat MSS, it's 80 meter pixel. It's a Landsat MSS, it's a multispectral scanner. That's the first commercial digital satellite in the world. The first images come from 1972, so it's almost 50 years of history. So it's like a road we've gone through for those almost 50 years. So wow, quite a change. Actually, there are also satellites of much lower spatial resolution, like hundreds of meters and even several kilometers. And it doesn't mean, of course, that spatial resolution, like the higher spectral resolution, is always better. That depends on what we need them for. If we need to see the shrubs, if we need to see the people or the rocks, of course, we will need very high resolution images. But if we need, for example, just to know where the forest is, it will be okay to use those low spatial resolution images. So it's not always the best way to use it to look for the highest spatial resolution possible. and also because those very high resolution satellites, the images, very high resolution images, are very expensive. They are only on for commercial use, so they are really expensive to get. Okay, the next thing, maybe not as popular, not as intuitive, but also very important, is spectral resolution. There we could talk about the spatial resolution, like what we can see, like how small or big objects we can see. But here, when we talk about spectral resolution, it's about what we can say about what we can see actually. So that's just to simplify it, that's a number and type of spectral bands, like we've seen before, those blue and green and red, etc. So this is what spectral resolution looks like in general. So when we, for example, when we use only visible bands, we can produce the image, the data like that, but with near infrared and then near infrared and short wavelength infrared, we can produce more data, more information about different aspects of the objects taken in this image. So it helps us to know the truth, to learn more about those objects we can see in this image. Here we have again Sentinel-2. As I said, that's very important today. So Sentinel-2 spectral bands, they are like in different modes. Let's say one mode is GSD, this pixel size 10 meters, but there are also 6 bands of 20 meters pixel size. So it makes 10, of course, and 3 additional 60-meter bands. They are not actually to get information on the objects, but rather for some corrections, for like atmospheric corrections. But well, they are there. So in general, we have like 13 spectral bands in Sentinel-2. What's okay? And we call such a kind of imagery multispectral imagery. So we have different spectral bands, like from several to like a dozen of bands. But we have also something called hyperspectral imagery. It's less popular, but it might be very useful. So when we have like tens or hundreds of bands, and they are very thin, because those multispectral bands here, they are like from, for example, like we take all blue at once, so it like from 400, for example, to 500 nanometers. But the length of those hyperspectral bands are much smaller. It's like, for example, from 400 to 403, from 403 to 405, and this way we produce much more information, much more data. We'll talk in a second why it might be important. So let's look at like typical multispectral bands. We have 3 visible bands, 1 near infrared bands, 2 middle infrared bands, and well, that's like, for example, Landsat have, and Sentinel-2 has something like that as well. So taking an image like that, those dots showing us values of one particular pixel. So we have pixel who has like this reflectance, like when we look at that. So that is an information we can get from those images. Nothing between, of course, because we don't have any information there. So we can create some, well, let's call it characteristic of this, like a profile of this object. It's not very precise. It's quite rough, but it's actually might be enough. I could say here easily that that's a vegetation, because it reflects more in green, and a lot of here, lot of near infrared, etc. Here again, very rough, but we can see that's a bare soil. This is a water. So again, this kind of information is in most cases is sufficient, is enough. But sometimes we need more detailed information. So that's why we could use hyperspectral imaging. So a lot of bands, very thin bands. And why would we need that? For example, let's imagine that we're looking for some specific mineral in water, in the soil, whatever. So it has some property that it reflects more radiation, but in a very thin band of the spectrum, like for example from 600 to 602 only. So if we take a multispectral imagery, we couldn't see this change there. But when we have those very thin bands, we can see that in one particular band, this exactly from 600 to 602 nanometers, there is a change. There is a peak. There is a bigger, higher reflectance. So this is how we can well find this mineral there. Well, so this is spectral resolution, and characteristics created this way are much more exact. And sometimes, of course, we need it, sometimes we don't. And next thing, temporal resolution. But basically is how often we can take an image of the particular part of the Earth. Here we have some well, like a fly of the calendar. During this month we took 6 images of particular, well, some location in Poland. So here, and here, 6 images. So this is one thing, but another thing is how often we can use those images. Here we can see, because there are actually those images put there in those boxes. So here we can see that there are just clouds. Probably in Madrid you don't have this problem as important as in Poland, but well, in Poland it's quite serious. So actually we have taken 6 images, but we can only use 3 of them. So it affects, of course, the temporal resolution. So it might be affected this way, of course, but it also must be improved. So it's not only how often the satellite goes over the object, over our location, but we might improve it. We might improve it by, for example, altering the optical axis. So let's imagine that we've taken today an image of Madrid, and we will need it tomorrow. But the satellite will be over Madrid not tomorrow, but in 2 weeks, for example. But we cannot wait. So we just like fly over, I don't know, Portugal, Lisbon, somewhere else, and we just like alter using mirror or whatever, alter the optical axis, and we take from over Lisbon, we take the image of Madrid. So that's one way to improve, to increase this temporal resolution, but also simply by increasing the number of satellites in constellation. So that's as simple as that. So for example, Sentinel-2 has, in this constellation, has 2 satellites. So thanks to that, we can get images twice as often, of course, as using only 1 satellite. And the fourth of those radiometric of those resolutions is radiometric resolution. That's probably the less important thing. Actually, it's quite important, but I mean that the standard nowadays is high anyway. So there won't be, you know, big changes, big differences between different systems. So radiometric resolution is like how many different values we can assign to pixel, how many different like levels of the reflectance we can write down in the pixel. Well, the standard nowadays is like 11 bits or 12 bits. So it means that we can write 2048 or 4096 levels. So it's much more actually than we need. When we look at the image like you're doing now, I hope, we use only 8-bit pixels. Of course, 3 times 8-bit, because we have like 3 different colors, red, green, and blue, because I suppose we see it in color. But every image is only 8-bit, so it's only 256 levels, and even that is much more than we need actually. Our eyes, our minds. Here we have 8 different images. Actually, that's the same image but degraded to different radiometric resolution. This one contains 256, that's 8-bit, 256 levels. This one only 128. This one only 64, 32, 16, etc., etc. So of course we can see easily the difference there, but well, here it's not so easy to see those differences. So actually we don't need our eyes, I mean, we don't need to visualize it. We don't need as many so many levels to visualize those images, but we might use it for calculations, for machine learning, for digital processing in general. So well, but as I said, standard nowadays is very high, so that won't be a huge problem, I suppose. Okay, we have in this presentation some self-assessment questions. We'll skip it because that's for you, like for the future. Like when you can download, of course, this presentation and then try to get, if you get all this important stuff from the presentation. There will be also some useful links for next parts. Okay, so let's go to another different kind of imaging, of remote sensing, radar imaging. So radar remote sensing, that's a completely different part of the spectrum. We had here like from 400 nanometers to like, I know, 1000 or 2000 nanometers. Here we have centimeters, from like 3 centimeters to 50 centimeters. So completely different wavelength with completely different properties. Before we start, you probably find this acronym SAR. It's like, well, like synonym of radar, actually, of remote sensing radar. It stands for synthetic aperture radar. That's because we synthesize those apertures, those antennas, because this length of antenna affects spatial resolution. The longer antenna is, the higher spatial resolution is. So we just synthesize this antenna just by by collecting, by synthesizing those signals from different parts of different positions, locations of the radar of an antenna, actually. So that's it. We won't go into details, but we compare a bit radar images to optical images because they are completely different. They have, as I said, different wavelengths. So by that, they have also different interpretation. Whatever we can see, that's completely different thing that we could see in optical images. And also they have different geometry, like different geometry of recreation of this image, of generation of this image, and that all of that make those radar remote sensing quite difficult thing. I don't mean like it's not a research problem, like not scientifically difficult, but there is some technical issues there. So it's quite like challenging, I'd say. Well, but there are also very interesting perks I want to talk about. So first one is that cloudiness is completely irrelevant. Well, almost completely irrelevant to radar images. This waves, this length of waves is completely insensitive to cloudiness. So we can get those images more often, with higher temporal resolution. We don't need to bother clouds anymore, actually. That's the first thing. And also radar images are active systems. That means that they emit the signal first, and then they receive this emitted firstly signal. So we are independent completely from external lighting conditions. We can take radar images during night, during like clouds, I said, well, whenever we want, actually, it doesn't matter. And of course, we couldn't do it with optical images. So that's a very interesting thing. That's very useful perk of radar images. Also, different, well, because we don't have like blue, green, etc., but we have different bands as well, like X, C, L, and P. So different bands can penetrate the vegetation, and this P band, the longest one here, could even penetrate the soil itself, especially when it's dry. So, for example, using that, we don't care if the soil, for example, if you want to get some information on soil, we don't care if it's covered by vegetation or not. Using, for example, L or P band, we can get like through the vegetation and get the data on the soil. So that might be useful as well. Quite important thing. I don't want to again, and well, I'd love to actually, but we don't have a time to go to details. But every image, every signal emitted and received by antenna is polarized. That's quite important. Quite important property of the image, of the radar remote sensing, and it can be polarized vertically, like we can see here, or horizontally, like here. And then again, as I said, we can polarize emitted signal and then received signal, like independently. We can polarize it the same way, like here, vertically, horizontally. We call it co-polarization, and we can polarize it differently, like here with cross polarization. So it's quite an important thing, because different types of polarization respond differently to different classes of objects. Those classes of objects, I mean different like geometric properties of those objects. In a few minutes we will go to that. Here, this is a cross-polarized image, and this is a co-polarized image. So we can see that it's different. So it means that the information here, it's like complementary. That's a different information. We get more information using multipolarization. So there are some systems can get us only one polarization at a time, and that's mostly only co-polarization, like here, for example. But there are also systems that can get multipolarization, like two polarization at once, like Sentinel-1. That's again European radar satellite. So we can get those two types of images. But there are also systems that they can get all four possible, like VV, VH, HH, and HV. So every single like type of this polarization get us different information. So that might be very important for our purposes if you need to use this kind of image. Of course, we can combine it in this way, like in a color composition again. So we have like different objects, and we can see how differently it looks. So every color is something different actually. Okay, I told you about different interpretation, that there is different interpretation. So the most important thing we can learn on the objects analyzing those radar images are the electric constant. That means how good conductors the object is. So good conductors reflects more of this radiation. That's the first thing. So, for example, metal objects or dry object, moist objects like moist soil will be brighter than dry soil. Next thing, roughness. We'll talk about it why, and orientation relative orientation to antenna. About this roughness, why it is important. Here we can see how different like geometric conditions, geometric properties of the object might affect the reflectance. Because what is very important, due to those geometric differences, we always take this image like from the side. We call it side-looking radar, SLR. So because of that, when we have like completely smooth surface, like for example, let's imagine water, which is a very good conductor, so it reflects like 100% of the radio waves, but because it's smooth, when it's smooth, of course, it will be reflecting it in completely, let's say, wrong way. So nothing will go back to antenna when the surface is smooth, even if it reflects like 100. So this rougher surface, when we can see some scattering and some part of the signal returns to the antenna, this rougher surface will be brighter than smooth surface. Also, we have different kinds of, like here, double bounce. For example, let's imagine that the wall of the building and the ground, of course, so we can see something like this. And this kind of reflectance will be especially, like well seen on those co-polarized image when we have like VV or HH. So for example, like built-up area will be very bright in this kind of images. And for a change, when we have like vegetation, trees and wheat or whatever, we have something like volumetric scattering. So it will be, for a change, well seen in this cross-polarized images. So it's VH or HV. So by that we can also interpret what's the object, what's the kind, what's the geometric properties of the object, and basing on that we can interpret what's actually it is. Yeah, so it sounds like that. But very important and quite unique thing about radar satellite, about radar remote sensing, sorry, it's radar interferometry. It bases, of course, on interference of waves. So as you can see here, we throw 2 stones into water, and they make waves. They are the sources of waves, and those waves might enhance each other when the phase is like the same, and they might suppress each other when they are opposite. So we probably know this phenomenon. So here we can see those interference of the waves. So the same way we use this phenomenon with radar interferometry. So when we have waves like in the same phase, they enhance, and we have the phase in opposite phase, we see that they are suppressed. So we just like throw one stone, one satellite as one source of waves. We throw second stone, second source of waves, and we can see that there are parts where they are enhanced, where the phases are the same when they meet, and sometimes the phases are completely different when they meet. So we have suppression there. And let's imagine that we have a ground there. So by let's simplify it a bit, but like we can take a photograph, like a radar photograph of this phases changing from enhancing to suppressing to enhancing again. We can build something called interferogram, like this one, and then unwrap it in quite a sophisticated way. That's quite a challenge, as I said before, and build, for example, digital terrain model. Not perfect here, but built anyway. So we can create 3-dimensional data on that. Even more interesting. Before that, there is a shuttle radar topographic mission by NASA, which provided us with this information, with this digital terrain elevation data, so-called, like a digital terrain model. It's not very detailed, as you can see. That's 90-meter pixel, but well, it's free and it's global, so that. Again, what's more interesting, I think, with this interferometry, we call this interferometry INSAR without those D in general. So it's SAR like synthetic aperture radar, and IN for interferometry. So it's differential interferometry. So it's DINSAR. How does it work? So again, we take an image, but we don't take an image. Well, we take, of course, the intensity. It's quite important here, but the most important thing is the phase. We register the phase. Where exactly what place of the phase we actually received back. So, well, we take it one time. Well, satellite is gone. Between the times something changed, there's some deformation, displacement, whatever, and again we are over this object, and we again take this image. Again, we receive and register this phase, but here the phase is different. So we can see that the phase is different, and basing on this difference in phase, we can calculate the placement. And actually, it's very, very accurate. This technology, much higher than this general INSAR we saw before, like producing only this digital terrain model. So digital terrain model might be produced this way with this approach, with like a few meters accuracy, but this differential interferometry has much better, even millimeters. So it's very useful, quite a challenging, as I said, but very useful tool of remote sensing data, radar data. Okay, so a few words about thermal imaging. That's also infrared. We call it infrared, but it's thermal infrared, so it's completely different thing than infrared. Just look, what time is it? Okay. We'll finish in a second. So quite a different thing than this near infrared and this short wavelength infrared. It just called infrared because that. So actually, it's like a giant space thermometer. It's like that. So we can. What's important? We don't get it, because usually we register a signal firstly emitted by some objects, for example, sun or antenna, like for radar images, and then reflected from the object. But here we register the signal, the radiation emitted by the object. So we just can say how warm or how cold the object is. So using that, for example, we can produce some, I don't know, city heat maps we can evaluate the condition of vegetation as well, but with not very high spatial resolution. Actually, that's the spatial resolution of those images is much lower than this optical or near infrared images. For example, Landsat 8 has this pixel size for multispectral imaging 30 meters, but for this thermal band it has 100 meter pixels, so 3 times worse. And last thing here in this part, laser scanning. We can call it LiDAR, like light detection and ranging, like we have radar radio detection and ranging. So here we have LiDAR, light detection and ranging. It's basically, well, ranging especially. So we just emit the laser signal. After that, we receive it. We measure the time between emission and receiving this image, and this way, knowing very accurately position of the scanner of the satellite of the airplane. In the moment of emission of the signal, we can very accurately calculate the altitude of the object. So that's basically that. That's a completely different type of information, of course, than before. Also, there are some quite important and useful advances advancements in laser scanning. For example, well, that's like years from now. We can, for example, register multiple returns, multiple signals returning from one emission. So here, for example, we can see that first return was from the top of the tree, and the second last return was from the ground. So using that, that's another kind of information. We can say, okay, this is an object, probably a tree, and it's as high as we can see here. So using this this information, we can create some 3D models. Like using this first reflection, we can generate something called first digital surface model. It's like a terrain, but with all the objects on that. But using this last reflections, we can create something between digital terrain models. So it's only ground and this digital surface model, because we can easily find those trees using this last reflection. But of course, it doesn't work with buildings, with other solid objects. But we can quite easily filter them out, those buildings, so we can create real digital terrain models. So this is how we can use this information. But also there are some other features of this technology. For example, well, quite a new thing is something called full waveform LiDAR. So we don't only register like a first reflection and the last reflection, or like 5 between them also, but we register the whole function of intensity of the returns, how many returns there are. So we can create a function like here, and for different species of trees, for example, there will be different forms of those curves, of those like, well, forms, waveforms. So it might help us to classify actually the species of trees, for example. That is used for that. This kind of data goes in this form, in the form of cloud of points, actually, because every return has its three-dimensional coordinates. So it's like that. We can, of course, create a raster from it and like visualize it like that. And also we can use laser scanning not only for ranging, for this altitude thing, but also we can use intensity of reflection. There are even there's also, this is also an active system. So again, we are independent of external conditions, and this is an example of a multispectral laser scanner. This is also quite a new thing. It's like that's one of the first images, one of the first data sets like that, and it's from 2016 or 2015. I don't remember actually. I remember that we wrote an article about that in 2016 for sure, but probably the image is from 2015. So using this multispectral data and combining it with this altitudinal data, we might gain much more information on this object. So about laser scanning, about the accuracy of laser scanning. So airborne LiDAR is very accurate and might be very dense, even to like 10 points per square meter. So we can create really detailed models. For satellite LiDAR, not as good, but well, they can be, of course, useful for some other case of operations. Okay, so I think that this is it for the first part. So I just close this one. I suppose you cannot see it anymore. Okay, so let's have a 3 minutes break maybe.
Perfect.
Great. So I have.
Yeah, that's fine.
Sorry. Okay, it's fine. Okay, great. So during the break, drinking water, please think about your ideas. Think about what is interesting for you, because we really need this information to make better training for you in the future. Okay, so I'm off for like 3 minutes, and let's go back in. Bye.
Thank you.
Okay, so let's start. 4 minutes left. No, left. Past. So let's start with the second part of our presentation. In this second part, just please confirm that you can see it. Anyone? Can't you? Okay, something bad happened. Can we start the second part? Yes, okay, great. Thank you. So let's start again. It'll take some time. Okay. So in this part, so I won't ask again. I just hope that you can see it. If you can't, why it doesn't work? Because what? Okay. So if you can't see it, just let me know, and I hope you can. So in this part of the presentation, we'll talk about how to get information from the data. Again, after that, about the Copernicus program, which actually brought us here together, and we will show several examples of remote sensing applications. So how to get information? Why it is important? Because normally the data, well, satellite images are actually a data. We can say like it's a raw data. There are only pixels and only values of the pixels, so we cannot say actually, well, there is no information like a straightforward information that there is a building or there is a road and there is a tree, etc. We cannot get it like easily. It's not written down there. We have to process this data to get the information, and we can get it by different processes. We will talk about those three today. So first, visual interpretation or photo interpretation, that's the same actually thing. So it's the interpretation of what's in the image actually. So we just look in the image and we mentalize the information. So we create it in our minds actually, this information. Very often we go beyond this what we can see in the image. Sometimes we take some different context of the time of the place. So we take some external knowledge about that to make this interpretation better, more accurate. We use something called interpretation features. Of course, you probably know it, what you do when you see, but sometimes it's very helpful to like analyze how we can say what we can actually see, how we can say that that's a road, how we can say that that's a building, the forest, or whatever. So we use interpretation features, and they might be color or tone. This is a spectral feature, one of this, well, the only one spectral feature actually. So this is actually what's inside the pixel, what is already there. So the color, let's say, of the pixel. But there are also a lot of spatial features. Like it's not like only one pixel, but a group of pixels. So the objects have shape, they can have different sizes, they can have different texture, structure, neighborhood, etc., etc. So using all this set, we can interpret the image. So first, of course, we can say that, okay, this pink means something different than this, like orange, dark orange, and different than this, I know, green or cyan or whatever. And but that's just a color or tone. But also we can see, for example, here something. Okay, I will take this laser pointer. We can see something long and thin here, so it's probably a road. We can say we have some granulometric granule texture, so well, probably a forest, etc., etc. We have different features to know different properties of objects and to learn about them. As I said, we very often use something more when interpreting the image, so we can take into account some context like historic, physiographic, environmental, etc. And this kind of well, processing, it's not a digital processing, but it's processing, like mentalizing, it's processing, of course. So it's very accurate because we take into account a lot of different aspects, and even not only what we can see in the image, but it's also very time consuming. Even well, not the interpretation itself is that time consuming, because, well, like experienced, seasoned interpreter could like see and look at the image and see everything. But after that, we need to somehow like translate it to other people, to the computer. So we need to draw the lines, the boundaries of different objects, and that takes time. But also the interpretation itself takes time and takes our time, human time. So we prefer to do it like automatically, of course. So this is about photo interpretation. And the second way to get information I want to talk to you is is spectral indices. Spectral indices, or spectral index, is a calculation of different spectral bands, actually. So we use only those spectral features, spectral information. So it's like we take two or more spectral bands and we combine them somehow. We have different types of indices. Very popular: vegetation or biomass indices, moisture indices, soil indices, and many others. So let's start with these vegetation indices or biomass indices. They generally base on these two bands, near infrared and red. They are generated, designed to distinguish, to identify vegetation and to evaluate its condition. So let's look at this green drawing here, and this green line. This is a spectral curve of vegetation. So we can see that the contrast here between very high reflectance in near infrared and very low reflectance in red is quite a unique thing among those all objects we have here. So calculating in a proper way those two images, like for example, simply we can calculate the difference between the reflectance here in infrared and the reflectance here in red. So we will get much more of a difference, much bigger difference here for the healthy vegetation than, for example, bare soil ground here, brown line here. This difference here is much higher. We can calculate ratio of those two bands. Why not? So again, it's much bigger than for anything else. Also, when we look at this dry vegetation line, also this contrast is much lower than for healthy vegetation. So it's not only to identify objects, but also to assess, to evaluate the state, the condition of the object. So this is how they work. One of the most popular vegetation indices is normal difference vegetation index. its formula is very popular because it's very easy and very well, useful. So this NDVI stands for Normalized Difference Vegetation Index, of course. This NIR and R mean reflectance in near infrared and in red. So we simply take two images, one in near infrared, one in red. So we take these two bands and we calculate difference between them, calculate the sum, we calculate ratio of those two calculations, and that's how we create NDVI. As I said, that's one of many, like tens or hundreds of different biomass vegetation index, but it's probably the most popular. At least it's very popular, one of the most popular indices. So here we have like a red band here, so vegetation will be quite dark here. For example, we can look here and here, and here we have this near infrared band, so vegetation will be very bright for a change. So when you calculate them, we can get something like that. So the brightness here in this image means the value of the pixel. So the bigger, the brighter the pixel is, the higher value it has, and the more vegetation or the better vegetation, the healthier vegetation you have there. So that's the way it works. So as I said, it might serve us to evaluate vegetation condition, but also to evaluate biomass. We have a diagram here showing a relation between leaf area index, which is a very good estimator of biomass, and NDVI value. It's not perfect, as you can see, but it's quite significant. So using this NDVI calculation, NDVI index, we can evaluate biomass of the trees, of the crops, plants, whatever. Moisture index, for a change, well, they might and usually are basing on the same formula, but with different bands. They use very often, well, almost every time, they use middle or short wavelength infrared bands, because this particular band is very sensitive to the moist of the object. The moisture, the more moist the object is, the darker it will be, because the water in the object absorbs this band of the radiation. So as you can see here, dry vegetation will be brighter, will reflect more than the healthier vegetation, which will be probably more moist than this dry one. So well, this is how it works, and very often we also can use those indices to evaluate also the condition of vegetation. And sometimes they are even better than this indices basing on near infrared and red we've seen before. And as I said, there are many others. Like for example, here there is index for evaluating quality of water. This is quite a huge artificial lake north of the Warsaw. So well, this numbers telling us like we had like near infrared and red there, this NIR and R. So this is basically a wavelength of the band we need to use to calculate this this particular index here to evaluate the chlorophyll in the water. We can see here that those bands are very close to each other. They must be very thin if you want to calculate this index. We couldn't use like multispectral bands. We need hyperspectral data for that, because we need a lot of very thin bands to calculate this particular index. So we couldn't calculate it using, for example, Sentinel-2 data at all. Okay, so that's about that. about spectral indices. And let's go to machine learning. Machine learning is a concept to avoid our interpretation, to avoid our well, processing, mentalizing, etc. We just like to automatize this process, and that's why we use machine learning to get machine learn for us instead of us actually, and then to analyze the data. It bases basically on first memorization of patterns, of some signatures, creating signatures experienced before by the machine. We can deliver those patterns to the machine. We can show, for example, this class of objects should look like that, and this class of objects should look like that, and well, learn it. So we teach it. We teach this machine, and after that, when it learned all the things it needs, it's analyzing new data basing on what it learned before. So well, basically that's it. To understand how it works, it's quite important to introduce a concept of feature space. It's well, closely related to machine learning. So let's imagine we have an image here, 20 pixels. Each square is a pixel. Of course, we know it's a colorful image, so it consists of at least 3 images: red band, green band, blue band. So it means that every pixel has 3 different values: in green, in red, and in blue. So we might write it down like here. For example, that's a value of red band, that's a value of green band, and a value of blue band. We can put all those elements of our set, all those pixels of our image, we can put it in something called feature space. Feature space is a space when those features, when those characteristics of objects are coordinates actually. So we can, for example, have a 2-dimensional feature space here. So green values, red values. So when we reorganize this set, reorganize these elements of this set in a way like this, those values are coordinates showing us the location actually of the element, we'd have something like that. So it's quite easy to see that all the objects, all the elements of the same or similar properties will be located close to each other. So we can say that the proximity in this feature space is like a sign of similarity. So the closer the elements are, the more similar they are normally. Of course, we don't take into account any geographical location here. It's only in this feature space. So this way, so it's just a reorganization of the set, of course. But after that, when we have this set reorganized this way, we can, well, quite easily using different, there are like hundreds probably of different methods of well, maybe dozens, okay, of different machine learning methods. So we can, for example, group those pixels that are close to each other, similar pixels, or we can like divide the space like here and say, for example, this is a part, this is a group or a part of the space or a group of elements which are red. This is a group of elements which are orange, and this is a group of elements which are green. So we of course simplify this. We simplify this this set, but in a way we need. It's an information at last, okay, and it might be created automatically or semi-automatically. We just need to provide the pattern, or we need to get the machine, to let the machine learn it by itself. There are 2 different approaches. So it could be like that. So it's not those different colors of pixels anymore. There are just 3 classes using this approach. Again, like for photo interpretation, we can use different types of features in remote sensing. Of course, we talk about it. Actually, we'd love to make this machine learning process, this classification process using machine learning. So to tell what it is water, it is a river, it is a building, it is a road. We would like to make it as close as possible to visual interpretation, but it's quite hard. Well, we have those different types of features again. So spectral features, very simple to use. There are only pixel values, and that's it. That's all the spectral features we need, actually. That's all the spectral features we get, actually. So this is one thing, but that's only like we look at the image and we see only color. That's not enough. When we want to, for example, say if it's a building or if it's a road, that might be difficult using only spectral features. There are also spatial features like size, like texture, shape, etc. So to use those features, those spatial features, we need another approach, something called object-based image analysis. We'll talk about it later. There are also temporal features, like we analyze the temporal profile, how this pixel like changes its values during some time period, and also altitudinal data. We talked about it before the break. Like we could use like laser scanning data, for example, to add to it something. We will talk about every single thing now. So let's start with the spatial features. About the spectral features, that was something like we saw before with this 20 pixel image. So it's quite easy. But what about spatial features? Why it's so important? We've seen it, but let's imagine that we need to distinguish, for example, different classes. So basing on a color only, we could distinguish only yellow objects from blue objects. That's all we can say. We couldn't distinguish, we couldn't identify, for example, yellow circles or circles at all. But if you want to analyze it this way, if you want 4 classes like yellow circles, yellow triangles, blue circles, blue triangles, we need to introduce another feature, like one of the spatial features, like shape. And using shape together with the color, with the spectral features, we can divide the space into 4 groups, into 4 classes. So we can say, okay, yellow triangles, yellow circles, blue circles, blue triangles. Everything is settled. So as I said, we use it with spectral features because spectral features are very important always, or almost always. So we use it. Sometimes just they are not enough. Let's look at this example. That's the image of satellite image QuickBird, very high resolution image. This is this false color composition when the vegetation is red. So those red parts are some crops. These are some forests basing on texture. This is bare soil. This is built-up area. And look here that the color of this bare soil and this parts of built-up area are the same actually. We can see that. We can easily tell that this is built-up area, but we need to base on spatial features. We need to look at the object size, the texture of this part. So this is how we can tell that this is built-up area, not basing on a color. So basing our classification, when it's based only on spectral data, it might give us the result like that. So for example, this built-up area, it should be classified as gray, as built-up area, and it's misclassified as soil in brown. So we see that a lot of errors here. But well, for a change, this water here is the water. It's quite good. So sometimes spectral data is enough. Sometimes it's not. Very often is not. But when we introduce something more, some spatial feature, let's try it with textual data. It might not look very informative, but actually it is. And what's important, it's not anything external. We didn't take it from other sources. It just processed the image we saw before. So it just processed the source image. We didn't take it from anywhere else. And with brightness of this pixel, it tells us about the texture, about high or low texture. And if we combine this textual data, this particular image is something called granulometric maps. It's a result of granulometric analysis, but there are a lot of texture analysis actually. That's one of them. So when you combine this data, textual data with spectral data, we get results much better than before. So, and it's actually quite easy. If you want to compare, again, we can see that the spectral textual, meaning using spectral data and textual data together, gives us much better results. But that's just only textual data, and that's quite easy. But when we want to, that's quite easy to calculate actually, and quite easy to assign it to single pixel. So we can use like a typical classification, like we classified every single pixel independently. But when we want to use different spatial features, we need this approach called OBIA, object-based image analysis, or geographic object-based image analysis. It consists of two steps. The first step is the segmentation. So because in the beginning we have only pixels. Of course, pixel has its shape, has its size, but it's not any different than size and shape of other pixels. So it's not very distinctive. But when we segmented this object, when we create this image, when we create the objects actually, when we draw the lines, draw the boundaries, not by ourselves but automatically, of course, we can then classify the objects, not the pixels, but the object segments. Sometimes we call them super pixels, those segments. So there are elements we classified, but they are consisting of different. They consist of different pixels. So it might look like that. So this is a result of image segmentation. So here we have segments, and those segments, what's important, have shapes, have sizes different than other segments, different than other super pixels. So we can, for example, calculate different metrics of shape, different indexes, like here, and add those features, like we saw before, add those features to this general set of data, and this way the classification might be much better. Okay, next type of the information, temporal features of data actually, temporal features. So it's like a temporal profile of the object. So we look at the pixel or on the object. We might combine those different approaches actually, and we monitor how it changes throughout time, throughout the season, for example. It's very convenient. Actually, that's the only way to identify crops, for example, because when we look at the image once, only in one date, different crops, different species might look the same, but this is how they behave throughout the season, the whole season. That's what's different. So for that we need very high resolution, very high temporal resolution for this. We will talk about it in a few minutes. When we go to examples of applications, but just a small like theoretical example. We have an image from April here, from June, from September. We can see how it changed, of course, and it changed differently for different crops, different classes of land. This is quite a nice, I think, color composition. When we didn't compose different bands, but the same near infrared bands from different dates. So actually every color means different profile of this parcel, pixel, object, whatever. So this is how we can learn how we can get the information about crops, for example, but also other stuff. Why not? And for the end of this part, altitudinal features. So we can use LiDAR data as additional data source, as additional features, and again, we can use it together with spectral data. I mean, for example, we have a problem with classifying, I know there is a building with a roof covered with tarmac, and there is a road covered with tarmac as well. So they look the same spectrally, but well, when we take this altitudinal data, the height of the altitude of the object, we can easily say that the high one is a building and the low one is a road. So this is how it works. Okay, there are different approaches to learning, to machine learning. We won't go into details, unfortunately, because it's a very interesting issue, especially for me. Of course, when you're interested in that, please write me an email or just write it in chat box, and we will talk about it later. So generally, we have unsupervised classification or supervised classification. Unsupervised is like totally automatic, so we just let the machine to learn the patterns by itself. We call it sometimes data mining. So we can retrieve some patterns we cannot see, for example, or we just don't have time to see using those approaches. There are a lot of different methods like isodata, k-means, Kohonen networks, etc. But probably the more popular way to use this machine learning is to supervise this learning processes. So well, it's actually, when it comes to satellite images, it's quite easy. I just want to show you how easy it might be. Here we have an image of this strange color composition when the orange or this reddish parts are vegetation, and cyan parts are bare soil. So this supervising this learning means that we, as operators, we provide the machine with those patterns, and it's, for example, it might be as easy as that. So we just show the samples of different classes, some representative samples of these classes. So, for example, we show, okay, this is how water looks like. This is again how water. This is how bare soil looks like. This is how vegetation, low vegetation, forest, deciduous, coniferous, whatever. So we just show which pixels it should take to learn those patterns. We just show it to the machine, and after that, it creates something called signatures. There are different approaches, different methods, so it might be quite different thing for different methods. And after that, after this learning process, it analyzes all the pixels in the image and classify it to the closest one to the class, which is the closest to the pattern. So it might look like that. It's not perfect, of course, here, because it was like it took like 3 minutes probably or something like that. But it's automatic. It's very, very, very simple and very, very quick. Of course, there are a lot of different approaches, a lot of different algorithms. There are very simple algorithms like minimum distance or k nearest neighbors, which are very intuitive, but very ineffective. Like it bases only on this proximity as a as a sign, as a signature of similarity, and it's actually, well, easy to understand how it works, but it's not always the proper way to use it. But there are much more advanced ways, much more advanced algorithms like random forests or support vector machines, SVM. They are much more effective. So basing on smaller data, learning data, they might provide us with much better results. And also there are very complex, very complicated, very difficult to understand, but very powerful. Well, they can be very powerful, very deceiving, like deep neural networks we probably heard of. If not, it's like a big thing now in machine learning, deep neural networks. So it's like that. So end of this part, and let's go to Copernicus. And we have, okay, we have some time. And okay, we call it Europe Size on Earth, and actually it is what it is. That's a program managed by European Commission together with the European Space Agency and together with all the European Union member states and some other European organizations like them, listed there. It consists of two components: space component and ground component. The first component is responsible for acquisition of data, and the second component for its storage and processing. So the first component is data acquisition component, space component. It bases mainly, not only, but mainly on those Sentinel satellites, the Sentinel satellites family. There are 6 types of Sentinel satellites planned for now. 4 of those types are already in orbit, 7 satellites. So we have Sentinel-1, which is radar. We talked about radar satellite. Sentinel-2, which is optical satellite, and also we have 2 other 3 and 5 satellites for now. We have also different services of like already made, ready to use products. So 6 different services dedicating to different issues. So there are not like raw data like images, like satellite data, but already products we can use. For example, the CAMS, which stands for Copernicus Atmosphere Monitoring Service, it provides us with information about pollution of atmosphere for every date we want, actually. So we just choose the day, we choose the factor, like here, particulate matter and carbon monoxide, for example, with different dates, as I said. So that's one. Many others as well. You can just go there and look for what you need for. Also, another one, CLMS, which is Copernicus Land Monitoring Service. There are a lot of different products. One quite an useful, important product is Marine Land Cover, the CLC. It's a map consisted of 44 classes of land cover for different dates as well. So we can just open it in some Explorer, some web application. We can also, using some web services, we can use it at our own computers, in our programs, etc. So we can like browse through different dates, through different places, etc. Also, some other products like high resolution layers. That's quite the same thing, but with different types of like more specific information on imperviousness of the ground, forest, grasslands, water, etc., etc. So just to take and use. Actually, it's ready to use. It's a product. It's not a data anymore. That's information. Well, so that was about Copernicus. basics of that. And I would like to show you some example applications of this data. So there are like really vast fields of possible applications of remote sensing. I would like to present you, well, briefly, few of them. Like here, for example, for the agriculture only, we could dedicate like I don't know 5 hours of talking only about how we can use remote sensing in agriculture. So it's really a long list of potential applications. Only small short list here. Let's start with precision farming. That's quite a new idea, of like 1,000 years, and it's a concept. It's an approach to farming when we don't when we use our works, our products like fertilizers, like plant protection products, only in the amount needed when and where it's needed. So to do that, to apply those products precisely in the amount we want and in the places we want, locations we want, we need the precise information on the condition of soil and data as well. So for that we need also remote sensing data, remote sensing images. For example, those biomass indices, those like NDVI, normalized difference vegetation index. So using this information, we can calculate some models to create something called application maps, which tells us where to apply which product in what amount. So well, after that we do it actually, and after the whole process, we can also monitor the yield to get some feedback on how much we get from the field. So using this information, we can, for example, analyze those models and maybe verify them and change them in a way. So that's how we close the circle. And in the circle, remote sensing data is crucial, is very important. So this is one of the applications. Crop identification, I told you before, it needs very high temporal resolution, the highest temporal resolution possible actually. So we have 3 different crop types here in the same time series, and we can see that's again this image where the red means healthy vegetation. So we can see how it changes differently for different crop types. So analyzing those patterns, analyzing those temporal series, those temporal profiles, we can get the information on crop types. Not well. Sometimes it's easy, sometimes it's not. But this is how it works. We can use it. Actually, this temporal resolution is very, very important. So very often we use radar data, radar images, to fill the gaps, for example, caused by clouds, to make this temporal resolution as high as possible. So analyzing this data, we just get what we want. Actually, I mean crop types. Well, another way to use remote sensing. Of course, we know that we can, using satellite images, we can analyze crop condition. That's what we know. We can use, for example, vegetation indices to do it. But what's important, especially when we use those Sentinel data, because what I forgot to say, and it's very, very important thing, that Sentinel satellites takes image continuously. So from the start to the end, they will take images about the whole globe, actually about the whole land or whole water or whatever, and all this information, it's stored in the hubs, so we can get them. We don't need to, for example, order them. So we know that we will need it in a week or in a month. We don't need to know it in advance. We need an image from like 2 years ago. We get it. We just look for that in the hub, in the application, and we get the image. So for example, here is the image after some bad wintering, I suppose. So this is NDVI image. Those brown parts means bad condition of vegetation, and this green means better condition, of course, and yellow something in between. So we have it after the winter, so we can see that there are a lot of damaged parts of this parcel, but we can also use the image. Well, we are in May or in April of 2018, and we can look back. We can use the image from January, but we can use also the image from November last year. So, for example, here we can see that was in a good condition before winter. It's in a bad condition after the winter. So it was probably bad wintering, some freezes. But when we look at this red arrow, sorry, we can see that this was bad condition before. So, for example, for agricultural insurance companies, we can use this image to say, okay, that was bad before. We won't pay for that. We will pay for the places that were in good condition before winter. So that's another way to use it. Also, for some agencies like government agricultural agencies, we can practice. We can monitor practices. Agricultural practice. Again, we need some multi-temporal analysis for that, but the temporal resolution here is not as important as before. Well, it's quite important, but not as much. So, for example, because we can see everything is done in the field, like there was a tillage, there was a mowing. We can see the changes in the spectrum of this place. So we can identify whether it was done, whether there was some work, and actually when it happened. So it's quite useful for this monitoring of good agricultural practices. Okay, so that's very briefly about agriculture. And let's go to forestry, another vast field of applications. So, of course, we can monitor by, for example, classifying. We can monitor the area of forest. Like here, we have already made service. We can use for free. That's global forest change. That's not one of the Copernicus services. It's provided by University of Maryland. So we can look, for example, like information about loss, extent, gain. Like here for different years, okay, and we have information about tree cover in the forest. So a lot of information. That service bases on Landsat imagery. That's another very useful source of data because it's it's also free and free to use, and it takes images continuously. So we can go back even farther actually, because Sentinel started to work in 2015, Sentinel-2, and Landsat started to work. Well, there were a lot of generations, but the Landsat 4 and 5 are from like 80s. So we can go back really a long way back to like 40 years from now to make a very deep, like historical archival analysis. It's powered by Google Earth. That's one of the cloud platforms. We will talk about cloud platforms in a minute. And that's another application. That's a hurricane in Cyprus. That's not a very common thing. That was maybe not a very big hurricane, but because we don't have it in Poland much very often, so it was quite a big deal here. That's an image from before the hurricane. That's image from after the hurricane. We can see here that it's changed somehow. So that's the damaged forest. You can see it also on NDVI, which is probably more helpful. So we can see that there is a change darker now, so that means that there are no vegetation at all now. This vegetation is damaged. And using that, again, this part here, this is this damaged part, we can evaluate, we can calculate the area, etc., etc. And that's for, of course, that's a forest application, but that's also crisis management application as well. So we can monitor using satellite images occurrence and spread of natural disasters, which is very important because sometimes we don't have an access in any other way. We couldn't get this information. We cannot go there. We don't have cameras and anything there. We have to go to take this information from a satellite. So of course there are a lot of different types of events. Here again, forest, but fire this time. So that was quite a huge forest in 1988 in Yellowstone National Park, and that's an image from before. That's image from the year of the fire. We can see the fire spreading here, and that's the image from right after the fire, like the year after. So all those magenta, those pink or violet parts are actually burned. Also using satellite images, we can monitor how it changes and how it recovers as well. So those continuously taken images are perfect data source to do that. Another one, fire information for resource management system. That is a system which can help us to monitor the fire events, so different events actually. It's based on much lower spatial resolution, like we can see here. This pixel size is 375 or 215, so it's much less, much worse than we saw before. But for the scale of analysis is that's enough. It's sufficient source of data. Very useful for monitoring everything connected to water. Are radar images. So this is radar image, quite difficult to read. That's an image from before flood, and that's an image from during flood. What's important, very often when there are floods, there are also clouds, so we couldn't use optical images probably. So this radar data is a perfect data source, and also because we have this phenomenon we talked about, this mirror reflectance from smooth surface. Even if water reflects like 100% of this radiation, it reflects it in other way, in the wrong way, so it's black. So we can see it this way very easily. And quite interesting example of how to analyze the spread of the flood quite easily and in a quite smart way. We have a color composition here. When in blue we have before flood image from before flood, and an image from during flood, it's in green and red. So it will be like yellow together. So what we can see here, those blue parts, those blue areas are blue because they were bright before flood. They reflected something actually toward the antenna. They don't reflect it now. That means that there is water during flood, but there wasn't water before flood. So actually those parts are in fact flooded. Here, for a change, we have this black part here, this black river. It means that it was black also before flood. So it's not actually flooded. There is a water, that's true, but it's not flooded. So we can easily identify parts of this terrain, of this area, actually flooded. Or another way to use radar images for something connected, related to water. That's actually water, that's some land, that's also a water. These bright spots are some drilling platforms, metal constructions, so they are bright. And this black parts, like black, well, whatever, they show us where the oil is spilled. Those oil spills, actually, and how we can see it because of this phenomenon. Normally, in the ocean, water is like never or almost never smooth, completely smooth. It's undulated somehow. There are waves, so they make this water somehow like rougher, let's say. So it makes this wave, this signal, return partially, at least, to the camera. So it's brighter when it's undulated. But this oil spilled here increased the surface tension of the water, so it makes it smoother. So we have again this mirror-like reflection of this radio waves. So this is how we can use it. And the last thing in this part is infrastructure monitoring. Okay, we need to speed up. So I will be talking only about this deformation and displacement monitoring, this part, using this technology we talked about before, differential interferometry, radar interferometry, and especially the technology called persistent scatterers interferometry. It bases on some objects we can identify, like throughout the time, like the same objects, like buildings, for example, or any other persistent scatterers. Like, mean they are bright and they are persistent. They are always in the same at least relatively the same place. So using that, we can create like a cloud, like a map of points of the scatterers, and we can analyze the displacement formations of the terrain using that. That's one of the application, and some other application as well for the same thing. Okay, so that's it. So now go to the okay. Now I see that I need to apologize you for just a minute, because I have to okay, because my battery is low. Okay, now we save. Okay, there was a okay. And the third presentation, and the last one. That will be much shorter than the two previous ones. Okay, part 3, perfect. So we'll talk about DIAS platform, and then a few words about Galileo, about Europe's European satellite navigation system. So again, DIAS stands for Data and Information Access Services. The whole project, there are 5 DIASs. The whole project is financed by European Commission and the European Space Agency, and it changes the model, the way we use satellite data. Because normally, well, the traditional way to use it is like we have a data hub, we have a local environment, like local computer, and we download the data and process it like locally. But very often this data is like a huge amount of data, like terabytes sometimes. So it takes time to download it. Also, it takes infrastructure to build to store this data. So the DIAS concept is to change this approach, to change this model. So everything is actually made there. So we don't need to download the data. We don't need to process it. We don't need to store it. It's stored there. We process it there. So everything is online. We just need to order it and download results if we need to. And if we don't, we just can put the results, for example, in the web, some web application, whatever. This is, as I said, Creo DIAS is one of the 5 DIASes. It's created by the consortium listed of companies listed here. One of them was Creotech Instruments, partner of this project. So we have an access to data of all Sentinel satellites here. Also Landsat, but for Europe only, and some other satellite data, and some other type of Earth observation data, like digital elevation models, for example. So this is what we can get there, but also there are products of these services, so already made product, already ready to use. And as I said, we don't need to download it. We just use it there. We just use it like in the cloud in this hub in DIAS. And we can also use the software we know to use that, like ArcGIS, popular QGIS, and all the stuff actually we need. We can use it there. So we don't. We don't need to to download the data to process it in our software we used to. We can do it. We can do it actually there. There are a few functionality levels of Creo DIAS platform. The lowest one is a Creo DIAS Finder. It only helps us it serves to search for data. So we just choose the area. We just choose the collection. I mean the satellite type. We just choose the time range. Cloud coverage, that's a quite easy to understand interface here. So we just choose everything, and it shows us the list of products meeting our requirements. We set there. So that's the one way to use it, and after that we can for example, know what we need for our purposes. Another one. A bit higher, Creo DIAS browser. It's for searching and visualizing data. So we can again set the area. We can set the cloud coverage, the satellite type, time range, of course. But also we can then visualize this data in different ways. We have lists of prepared types of presentation, like true colors here or false colors we saw before, NDVI as well, already there. But also we can prepare our own band combination, our own color composition. Also we can calculate some indices we want. So it's quite useful to see actually what we need. Also we can build a front office, so we can create some application to present the data and maybe commercialize it if we want to. Like for example here, this again, this persistent scatterers interferometry we saw like a few minutes ago, presentation, Reticus platform based on Creo DIAS. So there is a film showing us how rich it could be, basing on this data on this platform. Of course, we can create maps, we can create different diagrams and whatever we need for different purposes, like this persistent interferometry or water quality evaluation, etc., of IAS here. So that's another way to use it. Of course, it's not free. Looking for data and searching for data and even downloading it it's free, but using it there, it's not free anymore. So we can pay per hour or even per minute. We can, for longer term contracts, we can fix terms, and also they have a revenue sharing model. If we want to commercialize, we just share this revenue with Crowd DIAS. So there are 3 ways to be built actually, and there are also other DIASs, as I said. There is a list of them, and other cloud platforms as well. But it's a good thing to remember that not all of them have an access to the Earth observation. This EO stands for Earth observation data. Actually, this is what DIAS are for. They are especially designed for this remote sensing applications to use it in cloud. So, well, Google Earth Engine have some really great features as well, but well, DIAS are especially designed for this purpose only, actually. Okay, so that was about Copernicus, and the very last thing I want to talk to you about is Galileo. Galileo, as you probably know, it's European global navigation satellite system. So it serves to navigation, of course, and it's interoperable with another global navigation satellite systems, American GPS, which are used to call all these navigation systems GPS, but that's actually the name of the American one, and the Russian GLONASS. Why this interoperability is important? Why it's important that we have our own navigation satellite system? Because, well, Americans or Russians, they could in a moment like turn it off, and we would be like blind probably. We couldn't know where to go, for example, when we don't know the city we're in. So this is important to have to be independent in this case. But also this interoperability is very important from the other reasons. Well, to show it, it's important to understand the very basics of satellite navigation systems. We need at least 3 satellites to localize the antenna, actually. But the more, the better. The more satellites we have, the better accuracy of the localization we have. But sometimes, and usually we have a lot of those satellites above the horizon, as we call it, because there are like always 6 or 7 satellites. For example, if you use only GPS. But sometimes when we are in in a town with high buildings or in a forest, the signal might be blocked. So using only one system, it will be impossible or difficult to accurately localize the antenna. So for that, we need other systems. So the more systems we have, if you can operate together with those different systems, we can get information from different satellites, different systems. So it's much better, much more accurate, and much more safe actually, to not lose the signal. Today we have 26 satellites in constellation, from which 22 are operational. The accuracy of this localization is publicly 1 meter, and there is also possibility to get this accuracy much better, but it's encrypted for some reasons. Of course, we can imagine what reasons. And last thing, applications of global navigation satellite systems are like a vast. That's an understatement. Of course, it's navigation of all sorts, like road, rail, maritime, for airplanes, for everything actually. But also for science, Earth science, since we can monitor change of the Earth, of the shape of the Earth, etc. but also some other things like surveying, of course, but games. Well, there was a very popular game called Pokemon Go, like a few years ago. So well, that was based on this global navigation satellite system as well. And just the very end of our presentation today, it's a simple presentation of some application created by Creotech. It's called CreoScan. It's like to program and to monitor the flights of the UAVs, of the drones. So we can see it here. We can, like, as I said, program it and then monitor if everything is okay, just to to make it completely autonomous this flight. So that's it from my side. I'm sorry I extended it to a bit, like, well, 2 minutes probably. Okay, I suppose you can see me again, not a presentation. So again, if you have any ideas about how you want to use it, and you want us to focus on those issues for the future stages of our projects, please, there is a time, and after that there will be time as well. So take a time if you don't have it like verbalize it now. But I will be happy to answer any of your questions. I don't want to extend it anymore. So, but if you have any questions, we may like switch to email in the future. I'm yours. Thank you. And I really trained like an hour and 55 minutes. I don't know what happened.
It's perfect. Thank you. Thank you for your interesting speech, Professor Cupidura. I have been a really pleasure learning from you.
Sorry?
I have been a pleasure learning for you.
Mm-hmm.
Thank you very much. If does anyone any short question, it's the moment. If not, probably can send an email or the professor. But if anyone has any question,
so I might write down my email here.
Perfect.
Okay, maybe I will give you the. Okay.
Okay, maybe in the chat box you can write your mail and.
I just wonder which one I should use. But okay, I will use the same. Oh no, I was writing it not in this.
Or
okay,
no
okay.
problem. Yes, no problem, because I can send your email at our attendees. Okay. Okay. Perfect. Perfect. Thank you very much.
Thank you.
Okay, we continue with the space soon. Gustavo Calauri is going to make a brief presentation about the space project based on Copernicus technology. Gustavo is a highly specialist professional in the management field with over 20 years of experience in direction and business management, a deep knowledge of business deployment with national and international expertise, and especially ability to open new markets and managing teams in diverse scenarios. Gustavo, thank you for being here and showing us your project.
Okay, thank you very much. I'm going to share my screen. It's okay now?
It's perfect.
Okay, well, excellent. Well, first of all, thank you very much to the organization on Go to Space to give us this opportunity to present our one of our solutions that we called EO for demographics. We are a company working in the EO arena, and we are specialized in software engineering and solutions applied to the entire aerospace cycle. And our mission is to generate a positive impact on business and society based on the application of space technology for digital transformation. We have offices and working places here in Europe, in Barcelona, Spain, and we have development platform solutions in South America, in Buenos Aires, Argentina. We would like to construct a bridge of technology and operations from Europe to Latin America, and from Latin America to Europe too. We held the certified positions just to develop all the solutions. And this is our business approach. We have three pillars of solutions and application: aerospace engineering, industry solutions, and educations. Now we have the support of Go to Space Hub in the acceleration process of the company and the solutions. We are in a scale-up point of the company and solutions, and we are very pleased and gratefully with the people of Go to Space to support us in this process. EO for demographic, it's an advanced Copernicus-based population estimation solutions, and this points to a more democratic, scalable, and sustainable solution thanks to Copernicus adoption. In this moment, we have a solution developed in the high resolution services, and now we are going to convert all solution into a Copernicus full services solution. And we are going to use multispectral and SIR data, the land monitoring services of Copernicus data, custom indexes, and local data. We are working to introduce the solution and the processing in a DIAS for accessing and processing of data in information and data. And the objectives is just to develop and to provide a microcensus and a statistical model population grid generation. Why this is very important? Well, the numbers speak by themselves. We focus the solution in the vaccine distribution services, and this is very, very important for most of the people in the whole world. One of the most important process for just to define the access in these services or in this process is herd immunity. That is applied to a simple formula, vaccines applied over target population. This is the main aspect of the solution. Get an affordable service even 5 years, as WHO recommends. Now, in the low-income countries, this is very, very difficult, and this is a big challenge that we can help to organizations to get it. For that, we defined a big market or a big target of beneficiary in the world, that is the low-income population countries. In this area, a lot of money it's managed every time to get and solve this kind of distribution and to help the people to get the information in particular. But this is very important for basinage operation. These are our customer target. And from the two aspects of the analysis, the top-down and the bottom-up analysis, we identified more than 500 million market to get in. And then we defined a pricing of $5 in square kilometer in rural areas and $50 per square kilometer in urban areas. That is our target of managing in the aspect of business. But it is very important for us and for the people in particular that it fit with the market. And we really certified that it fit, because the solution was currently validated with local authority, people from UNICEF in the headquarters in New York, and Gavi Expert, that is one of the very most important distribution basins in the whole world. It's an organization that manages most of the people in this aspect. We have a first success case deployed in Chad and Mozambique, and in particular, the numbers that we point to with the adoption of Copernicus services is just to define and to get the 50-time cost efficiency compared to the country census, the traditional country census, and expecting to read more than 200 times when using Copernicus data. This is the importance of this aspect, because this could help us to democratize this kind of services. And our success case was in 2018, when the UNICEF goes to the market with a tender, just trying to define a census in areas in Africa. They defined 2 areas, Chad and Mozambique, and we analyzed the services and we defined a solution out of the box. And we think that the supporting solution with Earth observation analysis and the supporting of new technology can help them to solve in a different way a very huge and complicated solution. And we got it. And this was our first case with UNICEF, and we developed and we are working with them in our EO-based methodology for the estimation of demographic variables. We use satellite imagery, computer vision, ancillary data, microsession services, and a statistical model. The pointing to in different addresses, in particular, one that I talked earlier, that is the aspect of low reduction in cost and very high efficiency in the frequency and the target for the basin distributions. The challenge lies in determining the geospatial coverage that correlates to the population variables that decide. This is achieved through the training of a statistical prediction model that uses Earth observation data and in situ microcensus to extrapolate a population grid. This is how we can modulate and extract data from the building and the aspect of the regional in areas, and we calculate the socioeconomic parameters to integrate in the algorithm. Then the results of the whole solution, it's a population grid. Another layer serves as data services. Then you can define an area, and in this area you can get the specific data that you need for the distribution and the information that was very useful to get the decisions in the vaccines applications. We can show this through a GIS interface for easy access, and we define different analysis tools and to interoperability and to interconnect all the aspects of the information data. We construct an API to connect with different models in aspects of managing the data. The final result as information based on our own platform. It's called GeoPlatform. You can serve different layers of information, and you can manage all the GIS and all the data to supporting the monitoring and the information of this campaign. We have our go-to-market plan. The very first step is to improve and get the evolution and development with UNICEF and the Bill and Melinda Gates Foundation, that were the donors for this opportunity with UNICEF. And then we are going to engage more stakeholders in the process, like Red Cross, the PAO, the KB in itself, and we are going to participate in public tenders, outreach campaigns, and demonstration and workshops and webinars. And we are convinced that with the support of the people and the professionals of the go-to space, we can obtain this accelerate and the process and the improvement to get different aspects of markets and to scale up this kind of solutions in the space arena. We have different focus for this process. One is the benefit for the population. Well, the numbers speak by themselves, but one of the most important is that the vaccine saves life and money. But in particular, we need just to get an important aspect of a solution in the market arena. That is there should be a return of investment for the customer. And one of the most important is that the ROI for this kind of investment is for each dollar invest, the customer will return more than or almost $16 in return in healthcare cost, low wages, and productivity. Plus the centralization and normalization of data, the availability and interoperability, the better visibility of the situation, and increase the planning and decision making and tools to assist during campaigns. This is a huge definition and model of services that, for example, UNICEF doesn't have when they take the decision to distribute vaccines. And this was very important, and one of the aspects that they like in this aspect was the reaching of more democratic and scalable of the situation when they decide to invest in this kind of solutions. Of course, there are competitors, and we identify difference in the market, but we know, or we really think that we are best of the breed solution, because the integration of Copernicus and different aspects of local services and analyzing in the points of application. And then this was because of the 50 time cutting prices of the population estimation, and more than 200 cutting prices when we adapt into the Copernicus infrastructure. This is the importance of the process. We have our roadmap, and this year, well, the next year, in the final of this year and the next year, we are modeling of the solution into the Copernicus data, and with the DIAS integration, we think that we got the scalability that we are looking for to care of the solution for different customers. And the implementation of the RED protocol for the UNICEF, the RED protocol is the reach every district, and this is very particular, and this is very important aspect of the solution, because this will support all the process and all the integration of data and solutions in the whole change in the aspect of the vaccine distribution. Then we have a then we have a roadmap to process in next year, and this is a very important point, that this is not just for the vaccine distribution. This is think just to cover most of the necessities to distribution, for example, for water, for food, or for integration in geomarketing and definition for taking advance in the decisions of knowing the exploiting of the geographic and the population area in the whole world. Well, this is the aspect of the solutions, and well, I'm available to support with questions or sorry, I need to. Yep. Okay.
Thank you, Gustavo. It's a great 2-year project like yours, with a perfect mix between space technology and high social impact. We wanted to show an example, a case of use with Copernicus, and I'm sure that has been the perfect example to show the possibility of Copernicus. Does anyone have any question for Gustavo about this project? No? Okay, thank you, Gustavo.
Okay, thank you very much.
Thank you. And now is the turn for Elsa de la Haza. Elsa is responsible for managing and coordinating the Go to Space Hub hackathon, the first hackathon in 2021 around DIAS environment. So Elsa, it's your time. You can share your screen if you want.
Okay, thank you very much, Gemma. Good evening, everyone. My name is Elsa, team member of Go to Space Hubs and coordinator of the upcoming Go to Space Hub hackathon. Firstly, I would like to thank Gustavo from SpaceU for his presentation, and the Professor Cupidura for the training on DIAS. It was very interesting. I also want to close this session with an announcement for the next Go to Space Hubs activity that we are organizing on space technology. So I'll share with you a short presentation. I think now you can see the presentation. Tell me if it's okay for you.
Mm.
Yes. Okay.
1 second. Now.
Now? Okay. Great. Well, the aim of this competition is to promote the usage of DIAS platforms and Earth observation data that benefits for business ecosystems, researchers, and other users too. We would like to encourage you to participate in this upcoming hackathon that will be celebrated in February of 2021. A great opportunity to get together with a variety of experts, startups, scale-ups, companies, investors, and well, we will be able to solve challenges from the following thematic areas. This is following digitalization, related to big data, Internet of Things, smart city, smart transport, sustainable development goals, climate change, social impact, defense and security, fintech, big data, cyber security, and space tech excellence. I mean, well, space upstream and downstream sector. Please note that participation in the competition is open to startups, scale-ups, small and medium-sized enterprise, large company, entrepreneurs, researchers, and students from PhDs and masters, and investors too. So, well, your company, if you register to this hackathon, can be part of international mentors and experts pool, and a catalyst for agents from the space sector. Challenge solving. You can get great innovative solutions for great challenges. Visibility, the opportunity to get European notoriety for your project or company. And you can receive great training sessions on cutting-edge technologies from space and uses cases too. Well, how can you participate on this event? You can participate as a challenge owner. You will propose a challenge to be solved, and you will take part as a key agent at this event. You can collaborate as a participant during teamwork days into the hackathon. You will share your creativity and talent with others and get solutions for great challenges. You can participate as a sponsor. You will help professionals and teams at taking the first steps into the next level. And you can, if you prefer, participate as a speaker. You will be a reference of a good use case to inspire participants. So we would like to show you a draft of the agenda, which would have a welcome opening session. Then you will have training sessions, followed by use cases, then teamwork days, and finally the awards ceremony. So, well, you can register at this link. I'll pass you later on the chat box. Well, and for any additional information too, if you prefer, you can contact us at this email address. So that's all for me. If you any require or additional information too, you can tell us. And thank you very much for your attention. You look forward to seeing you all at the Go to Space Hackathon 2021.
Thank you, Elsa. Thank you very much. I want to share in the chat box the website of our hackathon. Okay. I encourage you to enter the... Yes, Manuel?
Thanks for sharing that. That'll be great. It's a great help. Thank you.
Thank you, Manuel. Thank you. I encourage you to enter on the hackathon website and sing on this event, because I'm sure it will be a great experience. Okay, any questions, any doubts, any suggestions? No? Okay. Elsa are sharing the email. Perfect. Perfect. Thank you, Elsa.
Thank you.
Okay, this is all from us. It has been a pleasure. Thank you all for the speeches, and thank you for attending the session. So I hope to see you soon. Thank you.
Thank you very much.
Thank you very much. Thank you very much.
Bye bye.
Thank you.